What specific problem does the Gaze-LLE model aim to solve in gaze target estimation, and how does it differentiate itself from previous multi-branch architectures?
The Gaze-LLE model aims to solve the problem of gaze target estimation by leveraging a frozen, large-scale foundational visual encoder, specifically DINOV2, to simplify the architecture and improve efficiency. Unlike previous multi-branch architectures that require separate encoders for head and scene analysis, Gaze-LLE integrates head position prompting directly into a unified decoder, eliminating the need for complex fusion modules and multitask objectives. This design choice significantly reduces the number of learnable parameters by 1 to 2 orders of magnitude while maintaining state-of-the-art performance across multiple benchmarks. Additionally, Gaze-LLE demonstrates that a powerful general-purpose backbone can effectively capture gaze cues without the need for specialized encoders, which often complicate training and reduce efficiency. Overall, Gaze-LLE's streamlined approach allows for easier training and better generalization across datasets compared to traditional methods.
How does the Gaze-LLE model work? Please illustrate its architecture step by step, including the roles of the frozen encoder and the gaze decoder module.
The Gaze-LLE model operates through a streamlined architecture that consists of a frozen large-scale general-purpose scene encoder and a learned gaze decoder module. First, the model takes an RGB image and a bounding box for a person's head as inputs. The frozen encoder, such as DINOV2, extracts visual features from the entire image, capturing essential scene information without any additional auxiliary models. Next, the gaze decoder integrates these features with a head position prompt to condition the outputs specifically for the individual in question. This decoder updates the feature representation using a small transformer module and ultimately predicts a gaze heat map, indicating the probability of gaze targets within the scene, while also determining if the target is in frame. This architecture significantly reduces the number of learnable parameters and simplifies the training process compared to traditional multi-branch approaches.
Can you provide a simple illustrative example showing a step-by-step execution of the Gaze-LLE algorithm in practice? What inputs would you provide, and how would the algorithm process them to produce the output?
To execute the Gaze-LLE algorithm, you would start with an RGB image, denoted as X_text IMG, and a bounding box for a person's head represented as X_text bbox. For example, if you have an image of a group of people and you want to estimate where one person is looking, you would crop the image to focus on that individual and provide their head's bounding box coordinates. The Gaze-LLE model processes this input by first using a frozen large-scale general-purpose scene encoder to extract visual features from the entire image. Then the gaze decoder module integrates the head position prompt and updates the feature representation through a small transformer, ultimately predicting a gaze heat map, H, that indicates the probability of each pixel being a gaze target. The output heat map can then be interpreted to identify where the person is looking within the scene.
What are the theoretical or practical advantages of using Gaze-LLE over traditional methods, specifically in terms of efficiency, performance, and model complexity?
The Gaze-LLE architecture offers significant advantages over traditional multi-branch methods in terms of efficiency, performance, and model complexity. Firstly, Gaze-LLE reduces the number of learnable parameters by 1 to 2 orders of magnitude, utilizing approximately 2.8 million parameters compared to the much larger models typically used in prior works, which simplifies the training process and enhances computational efficiency. Secondly, it achieves state-of-the-art performance across major gaze estimation benchmarks without the need for complex multitask objectives or fusion modules, demonstrating that a single frozen foundational encoder can effectively capture necessary gaze cues. Additionally, Gaze-LLE's streamlined architecture eliminates the need for a separate head branch, integrating head position prompting directly into the decoder, which not only simplifies the model but also maintains high accuracy. This design allows for strong cross-dataset generalization, as the model is less prone to overfitting due to its minimal parameterization and lack of reliance on auxiliary models. Overall, Gaze-LLE represents a more efficient and effective approach to gaze target estimation compared to traditional methods.
How was the effectiveness of the Gaze-LLE method validated? Discuss the datasets used, experimental design, benchmarks, and metrics employed to measure performance improvement.
The effectiveness of the Gaze-LLE method was validated through extensive empirical experiments on multiple datasets, including Gaze-Follow, Video Attention Target, GU-Reel, and Child Play. The model was trained on Gaze-Follow for 15 epochs and then fine-tuned on the other datasets, demonstrating strong cross-dataset performance without fine-tuning, which indicates its generalizability. Performance was measured using state-of-the-art SOTA benchmarks, specifically focusing on gaze heat map accuracy and the ability to predict whether the gaze target is in frame. The results showed that Gaze-LLE achieved superior performance across all datasets, surpassing previous methods, particularly in cross-dataset settings, where it exhibited better generalization and minimal performance drops. Metrics included pixel-wise binary cross entropy loss for the gaze heat map and binary cross entropy loss for the in-out prediction task, which simplified the training process compared to complex multitask losses used in prior works.
What limitations or challenges did the authors encounter with their proposed Gaze-LLE method, and how might these impact its applicability or future research directions?
The authors encountered several limitations and challenges with their Gaze-LLE method, particularly in leveraging foundation models like DINOv2 for gaze target estimation. One significant challenge was that a straightforward substitution of DINOv2 into existing gaze architectures led to poor performance, indicating that simply using a powerful backbone is insufficient without proper architectural design. Additionally, while Gaze-LLE simplifies the model by eliminating the need for a separate head branch, the authors found that the integration of head position prompts and the design of the decoder were critical for maintaining performance. The model also experienced a notable performance drop on the GU-Reel dataset due to a large domain gap and differences in annotation schemes, which suggests that the model may struggle with generalization in certain contexts. These challenges highlight the need for further research into optimizing the integration of foundation models and improving generalizability across diverse datasets and environments.